Hi guys, I'm giving something a try here. See if I can do this again. Since I can't be with you, let me push F5. I'm going to try to help you through the notes, and I hope that this is a help to you. We're starting section 2 for these 2 days that I'm gone. So we're going to take a look at the first part, if you will, please. And some of this you've already known before, but I want to go through in great detail to make sure we understand the different symbols. If you recall, we've already discussed X bar, where X bar, that symbol means the mean, and that it means the mean of the sample, right? Whereas the mu symbol, that Greek symbol, is the mean of the population, the larger population, okay? Now what we're going to introduce is mu sub x, which is the mean of the probability distribution we are looking at, where x stands for. That's the one we learned in section 1 yesterday, I guess, with you. Okay. I just put up here for you to see, recall that the X bar is the sum of all the X's divided by the number that you have, and the variance, not the variance, we're going to get to that next. Whereas little n is the number in your sample, and capital N is the number in your population. Okay. We did talk about standard deviation symbols. S is for the sample, and sigma is for the population. Okay, and now we're introducing sigma sub x, which is the standard deviation of the probability distribution. Okay, we're going to calculate these in an example in just a minute. And again, I put the formula here for you to remember what the formula was for that, for the sample. And then, of course, we're just replacing that with capital N. We're not minusing 1 there because in the population, you would know the entire population. Okay. You also know that S squared is then the variance, and sigma squared is the variance of the sample and population. We have sigma squared sub x, which is the variance now of our probability distribution x. Okay, sorry, there's a printer going on in the background. I hope that doesn't disturb you guys, but just keep listening here. I'm doing this at home, probably not the best place, huh? There's your symbol for the variance of the population and the sample size. Okay, so just keeping these symbols straight is important to know the difference. And I think we already do. We're just introducing the sub x ones. Okay, so let's take a look at this. The mean is also called the expected value. It's what you would expect to get from your probability distribution. The mean of x, sub x, that's the mean of the probability distribution. And this is also written E of x. And there's the fancy dancy formula, which means nothing more than you take every value from your probability distribution table and times it by the probability of that one happening, and add all of that up. We're going to do an example in a second for you to see it. Okay. And remember that your probability should all add up to 1. If it's a true probability distribution, all of the individual ones add up to 1. Okay. The variance is similar, where we're going to remember the variance is the difference from the mean. So as you can see here, you take every individual x value from your probability distribution table, subtract now that expected value you got up above, the mean of x, sub x, subtract that from each value, and then of course square it, and then times it by the probability for each. Okay, so this is what it looks like broken out. X1 minus the expected value squared times P1 plus X2 minus mean sub x squared, P2, etc. Okay. And of course, the standard deviation is that same thing, but now the square root of it taken. So you're going to be asked to find the expected value of a probability distribution, the variance, and the standard deviation. These are your formula to practice with. So let's do an example. So here we all like pizza, I believe. So X is the number of toppings on a pizza. And here's your probability that you get. 30% that you have 0. So it's an all cheese pizza only, right? 30% that you get 1 topping, or 20% for 2, etc. They're listed there for you to see. Okay, we're going to make our distribution table, very important. We practiced making those. You need to make sure there's your number of toppings across the top, 0, 1, 2, 3, 4, and then the probability of getting each of those underneath it. And notice that adds up to 1, right? Got a true probability distribution here. All right, so to find the expected value or the mean of this distribution, notice that we have taken, I don't know if I can get my cursor here, 0 times the probability of having 0 toppings plus 1 times the probability of 1, etc., all the way across, adding that up. And the mean or the expected number of toppings on a pizza is 1.4. That's on average. Okay. So now we want to find the standard deviation. Well, we've just calculated this 1.4 here. So we're going to do 0 minus 1.4 squared times the probability of 0 using that first column of our table. And all the way down the line, 1 minus 1.4 times the 0.3 here, and then 2, 3, and 4. And we get 2.72. And of course, then to find your standard deviation, you take the square root of that variance, 2.72, and you get 1.65. So our probability distribution has a mean or a expected value of 1.4 toppings per pizza, but a standard deviation of 1.65 toppings, either direction there or that. Okay. A couple of things from the lesson about law of large numbers that you need to have in your notes and thoughts, and that is the larger the size of a sample is that's taken from the population, then of course the closer our sample mean will get to the true mean. The larger the sample it is. The smaller the sample, we're going to have a little bit more deviation from that. And recall, we have talked about this, recent history does not influence the probability associated with the next random variable selected. Just what has happened recently doesn't mean it's going to make it more likely on the next one. We talked about, I believe, the slot machines at the casinos. Okay, that just because it hasn't paid off yet does not change the probability of the next pull of the dial. Unless, of course, as Brandon pointed out to us, you've got some rigging by the casino. Okay, although selection without replacement does affect probability of the next item if our population is small. But think about this, if our population is really large, the fact that we did not replace one for the very next item is not going to have a huge difference. Let's say we had 1,000 items, okay? If my probability is that, 1 out of 1,000 times I'm going to get this thing chosen. Well, now I selected and I have 999 left. 1 out of 999 is not a huge difference from 1 out of 1,000. But if my population is small, 15 for example, 1 out of 15 is a lot different. Well, not a lot, but getting more different from 1 out of 14. And then the more variable the outcomes, the more trials, of course, we're going to need it to make sure our X bar gets close to the mu. So we need to do more sampling there if we have quite a bit of variation in our, I don't know, of course, this got cut out, didn't it? Oh, yeah. What I wanted you to do next is to discuss with your neighbor right now. And so I'm going to ask you to pause the video in just a second. And how do these things that I just shared here impact gamblers? Can I hide this? Yes, let's hide this. There we go. How does this impact gamblers? Talk about that right now with your neighbor. Pause it. And I'll be back in a second. When you're done, push play. All right, if you and your partner have had a discussion, you're coming back now. And here is the next piece of, this is kind of, for me, the fun part of this. And actually the Monday when I am back, you have a quiz, and this is on the quiz is to determine if a game is fair or not. We're going to use what we've just learned with expected values to determine if a casino game or any kind of game where you're paying money out to get money, if it's a fair game. Okay, of course, casinos are going to not have fair games because they need to make money. But let's just look at this. You're going to roll a die. To roll the die, you pay $1. You can win $5 if you roll a 6.